Hey, my name is Joshua Campbell, and this semester, myself, Vincent Holzenbeck, Frankie Reed, and Daniel Zitzmaster teamed up in Clemson University's Senior Design 2 to design and create the Angry Soccer Ball, a self-returning soccer ball. First, a project introduction. We realized that tennis players have it easy when practicing alone. They can hit the ball against the wall and it will come back to them. But for soccer players, with the most popular sport in the world, it's not this easy. They have to go fetch it out of the net every time. So our goal is to design a soccer ball that will return to the player. That way they don't have to keep playing fetch with themselves. And we wanted to keep this ball at a reasonable weight. So some of the constraints that we gave ourselves was the ball needs to be able to be kicked without permanent damage, and it needs to return within 3 meters of starting location after rolling less than 20 meters within 20 seconds of finishing its roll. And lastly, the ball must weigh less than 1 kilogram and must be cushioned or flexible to avoid injuring the kicker.
At the high level of our system's design, we have a TIVA microcontroller making decisions based on an inertial measurement unit, or IMU. When the soccer ball is kicked, the IMU's accelerometer registers an impulse, and the TIVA begins tracking position. When the ball comes to a rest, the TIVA uses servos to orient a two-axis gimbal so that the motor and its attached counterweight point back towards the user. It then spins the counterweight backwards, and the ball rolls forwards because of the conservation of angular momentum. When the ball is almost back to the user, the TIVA will turn off the motor and the ball will come to a rest. Here you can see the internals of our final prototype and can clearly see the gimbal composed of a black and gray rings. This two-axis gimbal will allow the motor to point in any direction desired. Section 2, Design Overview. Our system can be decomposed into 3 subsystems. The structure, 2 rings, lightweight, strong, plus an interior mount for motors and chips. We also have electrical hardware, a motor driver chip, the IMU, and the TIVA microcontroller, which controls the code and the ball. And finally, we have our software, which runs on that TIVA.
Many of the important structural specifications are listed here, and we rated them on our success towards the end. A lot of them were successful, getting the 2 degrees of rotation, making sure all the electrical hardware fit inside and wouldn't get tangled, being the size and weight of a soccer ball, the flywheel balancing correctly on the center of the motor shaft. And the big issues that we ended up having were assembly access, because there were so many tangled wires and moving parts. It was really hard to get in, especially if we needed to debug something. And the actual ability to roll. So the outer soccer ball shell that we put the device in was actually, we found out, too heavy to actually the flywheel to get enough torque to roll it. And so outside of the shell, it rolled properly, but inside it was unable to. So that's why those got those grades. Next, we're going to see a video of all of the rings moving to show that the electronic components all fit and do not get tangled, as well as a video of the ring structure rolling on the outer ring. For the electrical hardware, we had a TIVA microcontroller, which controlled 2 servos, and those were connected to our individual rings. We had our BNO 9-axis IMU that was attached on the same ring as the microcontroller, and that gave us our gyroscopic and accelerometer data. And the microcontroller also sent driver voltage, the 11.1 volt battery connecting to the motor. It controlled that. All of these devices were selected based on their size and weight. We wanted to make sure they could fit inside of the soccer ball, as well as keep it below the weight specification. And we also wanted to make sure that they were powerful enough to create enough torque, the motor for the flywheel, and the servos to move the entire ring structure. So based on those specifications, we picked our batteries. We used batteries that have been used in model airplanes. This battery was used for all of the control and servo power, and this 11.1 volt battery was used to drive the motor and the flywheel for increased torque.
I'm going to introduce you to the program flowchart. I'm going to provide a brief overview of how the program works, and then I'm going to discuss some of the challenges that we encountered while working on this project. First, the initialization stage. When the ball first turns on, it must initialize the TIVA microcontrollers modules on board, and it must initialize and calibrate the BNO 055 inertial measurement unit. Then the ball must wait for an acceleration impulse. Once the acceleration is above a given threshold, the ball is determined to be in the kick mode, where the ball will then read the acceleration every cycle and save it to an array. Once that acceleration is below a given threshold, the ball is determined that it has stopped. It then moves into the third and most complicated stage, the return stage. During the stage, it first calculates the distance traveled and the angle of travel. It then has to align the gimbal to that angle, and then it must rotate the main drive motor and track its position until it returns. Once that is complete, it then repeats the cycle. How do we do this? Well, the whole system is programmed in C using Texas Instruments IDE Code Composer Studio. The code is separated into the three main sections I described earlier. First, the pre-kick mode, where it's just stuck in an infinite loop waiting for a high acceleration. Then the kick mode, where it's constantly tracking its acceleration until the acceleration has returned to a low value. Then return mode, where it must track the displacement vector of the ball, find the angle of that vector, calculate the correct return orientation using that vector and the current orientation of the ball as read from the chip, the BNO 055 inertial measurement unit. And then it must move the servos to match that return orientation. And then the main drive motor must be turned on. Finally, it tracks its position on the way back, and then the user is expected to manually halt the ball using their foot. What were some of the challenges that we encountered while working on this project? First, we encountered tight space and weight constraints. This heavily impacted our motor selection, limited the ability of the ball to roll because of the weight constraints, changed the ring designs a lot to match these constraints, and it made wiring very difficult. We also attempted to use TPU, a flexible 3D printing material, for the first gyroscope rings. Unfortunately, this proved to be a setback because TPU simply took too long to print for the rapid prototyping that we needed to deliver a successful prototype. We constantly had to change our ring design. We iterated through 8 different design models before we landed on something that actually met all of the criteria we needed. Next, the system software testing required that CAD model, that system design, to be complete and integrated together. All of the other systems had to be completed and working before we could really test our software. This proved to be a big challenge because it pushed our software testing very far back. A few of our servos, a few TIVA microcontrollers, and the IMU were broken during tested for unforeseen reasons such as soldering issues and overvoltage conditions. Shipping times were a limitation when trying to replace these devices. We accidentally bent the drive motor shaft while trying to rotate a flywheel that was too heavy, and this reduced the torque for all of our future prototypes and our final prototype. Several software issues were encountered because the devices we're using are not very well interfaced together, and it's hard to find public code that does this. One of the main results of this issue is with position tracking. Typically, to get accurate position tracking out of an inertial measurement unit, you have to filter the acceleration data using something called a Kalman filter. However, we were unable to find one that was already implemented that would work on a microcontroller like the TIVA. This proved to be a severe issue and ultimately meant that position tracking was not in a place that we wanted it to be for the final prototype. And then finally, the wiring constantly broke during testing because of the repeated strains and stresses that the ball applied to the wiring harness. You can imagine there's not a single stationary part in our system. So having wiring stay together without breaking is a very difficult problem.
The results of this project are that the assembly meets all the physical constraints that we initially set, with the servos being able to independently control the rings, and the rings not interfering with any onboard electronics. Our gimbal system fits securely inside of the 8-inch soccer ball we purchased and weighs less than the initial 1 kilogram limit. The entire assembly is able to consistently calibrate even when power is disconnected and reconnected, and the counterweight creates torque in the intended direction to propel the gimbal system forward.
One challenge we faced was the physics of making the ball roll. We knew we wanted the ball to have a normal flight pattern and rolling pattern, and so the center of mass of the ball needed to be at its geometrical center. This left our only option for driving motion to be the conservation of angular momentum. We spin a heavy counterweight inside the ball in one direction, and the ball spins in the other direction. The challenge here was that the ball has a larger radius and therefore a larger rotational inertia, as well as the ball will most likely be heavier than this counterweight ring. This means that most of the energy from the motor goes to driving and spinning the ring instead of moving the ball. You can think about it. If the counterweight is too light, then the motor will reach its top speed too quickly and all the motion will be given to the counterweight. So it's important that we make the counterweight have as large as possible of a rotational inertia. This means we needed a large inner cavity to maximize the ring's radius and to make everything else as lightweight as possible to save as much weight as possible for the counterweight. In the end, our ball was not unable to roll. However, the drive motor did manage to roll the outer gimbal structure. And we're confident that without a damaged motor shaft, we could have rolled this ball. In conclusion, this was an ambitious project for 4 electrical engineers. We faced many unexpected challenges, and we learned a lot about what it takes to work as a team of engineers on a new topic, as well as we learned a lot about specific challenges associated with our project. In particular, I wanted to mention that we learned the importance of spare parts for everything. Between the motor shaft bending and various chips breaking, they're very important steps so you don't have to wait for shipping at times again. We faced IMU with its limited position tracking capabilities. And we also learned how important it is to integrate as much as possible throughout the process so that you can work in parallel instead of series. Overall, I'm proud of the progress we've made on this project and what we've learned.
If we were to work on this project in the future, we would first want to tackle the IMU position tracking challenge. At the beginning of the semester, we vastly underestimated this problem, and we would need more time, expertise, and equipment to solve this issue. We'd want to work with some mechanical engineers to do further structural analysis, such as increasing internal padding. And we'd also like to continue to reduce the mass in whatever way possible, but especially with our outer shell as it currently is, the moment of inertia is too high. So we'd like to figure out a suitable way to manufacture a lightweight shell for our gimbal system. We would like to also integrate all of the electronics inside into a single PCB. A lot of our issues came when every few days we'd have to redo the wiring harness because of the vibrations of the system, something would come loose. And on that same note, create physical wiring support to increase the stability during motion and reduce that vibration that I mentioned earlier.
Right.
Okay, so we're going to demonstrate that all 3 motors can turn. We're then going to put the cap on, and then we're going to put the ball on the ground, kick it a few times, take it off, and hopefully, if it's a successful test, we'll show that all 3 motors are still turning. So I'm going to let go of reset. So there you go, all 3 motors can turn. So now, if we drop this off, we should see that all 3 both servos and the main motor are still functioning as they are. So that's a successful test.